Hello, my name is Jason Krajewski. I'll be performing part one of Fukushima 12 years later as a oral presentation by myself and Delvin Glover. Part one of the presentation, we'll be going over the introduction, events, and emergency response failures. In part two, Delvin will be going over public health effects, nuclear power moving forward, followed by the conclusion. So an introduction. Overall plant design, you have 6 boiling water reactors designed by General Electric, 3 of those reactors being manufactured by General Electric, 2 by Toshiba, and 1 by Hitachi. Architectural design was performed by Ebasco, and construction performed by Kajami. Construction commenced July of 1967 for Unit 1, and all units were commercially operational by 1979. As far as boiling water reactors go, basically the reactor heats up the water to a nominal temperature and pressure of 550 degrees Fahrenheit at 1,000 pounds. The boiling water undergoes a phase change to steam within the reactor vessel and is then sent to a turbine for power generation. Used steam is then condensed by seawater and sent back to the reactor via steam-driven pumps to continue the process. There are also 2 steam-driven recirculation pumps to be used during shutdown for cooling purposes, although the seawater pumps that are used to provide cooling to the condensers are electrically powered only. This is a basic one-line diagram of the General Electric boiling water reactor with basic support systems. On the left, you have the containment building, which houses the reactor vessel, recirculation pump, as well as the containment suppression chamber. On the right, you'll have another building which houses the turbine generator, condenser, seawater pumps, and other systems. The location for the site was established in Fukushima Prefecture, which is similar to a state within the U.S., and it crosses the border between 2 towns. The 860 acre site was originally on a bluff over 35 meters tall, although during construction, TEPCO, Tokyo Electric Power Company, lowered the height to only 10 meters above sea level to allow the reactors to be built on bedrock to mitigate the effects of an earthquake and also to minimize the running costs of seawater cooling pumps. With the lowered height above sea level, analysis provided assurance that a constructed seawall would still provide protection from a design basis tsunami. Here you can see an aerial view of the site. The larger buildings on the center left of the image housed units 1 through 4, while units 5 and 6 are in the building's center right of the image. And you can easily identify the seawalls constructed to provide tsunami protection. Emergency core cooling system is provided to provide a cooling water to the reactor in case of an emergency. Multiple layers of backup systems are provided to ensure reliability. Redundancy is essential to cope with potential failures during emergencies. The first layer of the ECCS is the high pressure injection system. It consists of high pressure pumps that can deliver a significant amount of cooling water into the reactor vessel. These pumps are powered from a combination of battery banks and standby diesel generators if main power is lost. The low pressure injection system is the second layer of the ECCS and backs up the high pressure injection system. It also uses diesel-driven pumps or battery-operated pumps to inject cooling water into the core. The core spray system serves as an additional layer of protection in the ECCS. It's a network of spray nozzles designed to spray cooling water on top of the reactor core. This helps in maintaining the core's temperature within safe limits by providing a continuous cooling effect. And finally, these cores were equipped with a containment spray system. That involves spraying water inside the containment structure, which surrounds the reactor, to reduce the pressure and temperature within the containment and preventing the release of radioactive materials in case of an accident. Known as the Great East Japan Earthquake, this was the event that triggered the Fukushima disaster. On March 11th, 2011, at approximately 2:44 local time, a magnitude 9 earthquake occurred off the coast of Japan. It was one of the most powerful earthquakes ever recorded in Japan and one of the 5 largest earthquakes that has been recorded in the world since modern recording began. The magnitude 9 earthquake made it one of the strongest ever recorded, with the energy released during the event being equivalent to thousands of atomic bombs released instantaneously. The earthquake lasted for several minutes, with significant shaking being felt across a large area of Japan's northeastern region. Following the main earthquake, numerous aftershocks, some of them significant, continued to occur for days and weeks, adding to the challenges of recovery and relief efforts. The impacts were severe. The plant experienced intense shaking far beyond what it was designed to withstand, with the ground motion causing damage to critical infrastructure, cooling systems, and the electrical grid. Power was immediately lost, triggering a planned scram. This successfully shut down the reactors. The earthquake generated a massive displacement of water from a 20-foot upthrust of seabed, resulting in a powerful tsunami that struck the northeastern coast of Japan. The tsunami waves reached extraordinary heights and speeds, allowing it to travel inland, causing widespread destruction. Some reports indicating wave heights of up to 40 meters and the speed of the tsunami waves traveling an estimated 435 miles per hour. Residents of Sendai had only 8 to 10 minutes of warning to prepare. The tsunami waves surged nearly 3/4 of a mile inland, with the force of the waves sweeping away buildings, infrastructure, vehicles, and anything else in their path. The massive waves overcame the plant's protective seawalls and flooded the plant site. The flooding rendered backup battery and generators inoperable. The force of the tsunami also damaged the containment structures surrounding the reactors, compromising their integrity and making it more difficult to contain the release of radioactive materials. Surprisingly, no serious damage occurred to the reactors by the earthquake. All operating reactors were shut down automatically, although all external power was lost to the site. Emergency diesel generators located in the basements of the turbine generator buildings started up moments later. The first tsunami wave hit approximately 41 minutes later, and a second wave 8 minutes after that. The tsunami and resultant flooding submerged the condenser seawater cooling pumps as well as other auxiliary cooling circuits, specifically the residual heat removal system. The flooding also drowned out diesel generators, batteries, and switchgear, leaving most of the site in a total blackout. To make matters worse, the tsunami damaged roads and piled debris everywhere, making outside access difficult. Without decay heat removal, the situation became dire. Steam built up within the reactor vessel and was released via safety valves. As water level dropped, it uncovered the core after approximately 4.5 hours. The exposed fuel temperatures rose to an estimated 5,000 degrees, melted, and piled into the remaining water at the bottom of the reactor pressure vessel. All the while, hydrogen was being produced due to the zirconia cladding interacting with the steam. After approximately 25 hours, enough hydrogen had collected on the service floor above the reactor in Unit 1 and ignited. This blew the roof off of the building. 2 days later, another explosion occurred, this time at Unit 3. Initial reports were also a hydrogen explosion, but investigators are still attempting to identify the cause because of the completely different explosions. Unit 3 was much more violent and demolished much of the building with heavy black smoke. Watch below as the 2 explosions are shown individually and then compared side by side. Failures were being identified early in the project. It was during construction that engineers identified a concern with the plans provided by General Electric. The plan specified placing the emergency diesel generators and direct current batteries in the basement of the reactor turbine buildings. The engineers were concerned that this location would make backup power systems vulnerable to flooding, although TEPCO decided to strictly follow the General Electric designs during construction. TEPCO has been widely criticized for many failures and shortcomings, including inadequate risk assessment and not planning for a more severe earthquake and tsunami, a lack of preparedness, including emergency procedures, evacuation plans, communication protocols, insufficient safety measures, such as the height of the seawall, and prioritizing cost-cutting measures over safety. Even to this day, they are being criticized because of management of contaminated water. As far as the office of the Prime Minister, one of the primary criticisms was the perceived lack of timely and accurate communication to the public and local authorities. There were delays in relaying critical information about the severity of the situation and the potential risks associated with the Fukushima accident. The Prime Minister's office faced challenges in coordinating the response efforts among different agencies and organizations. There were instances of poor communication and coordination between the Kantai and nuclear regulatory bodies and TEPCO. This resulted in delays and inefficiencies in implementing necessary measures to mitigate the consequences of the disaster. Critics also argued that the Kantai had close ties to the nuclear industry, which raised concerns about possible conflicts of interest in prioritizing economic considerations over public safety. Fukushima Prefecture faced criticism about the effectiveness and timeliness of the evacuations and sheltering of the local population. This resulted in prolonged exposure and higher doses. They also were criticized by residents for poor communication relating to evacuation zones, radiation risks, and protective measures. These issues led to confusion and anxiety, which could have been minimized. The prefecture was also responsible for coordinating decontamination efforts. A large criticism has been the speed and effectiveness of the process and the long-term sustainability of the efforts. This concludes part 1 of Fukushima 12 years later. Please find part 2 performed by Delvin Glover.